Audience est en français? Okay. So for those that really want to know in English, we are going to have also a presentation in English. Là, je parle en anglais, excusez. OK. Donc, je voulais juste vous dire, on a inversé les présentations parce qu'il y avait un petit problème. Donc, on va avoir Maïté, en fait, de VAO, qui va présenter. Et ensuite, on va avoir Stéphane Meboun de Nellie Technologies. Juste pour les présenter tout de suite, dans le fond, Maïté, tu travailles depuis 9 ans déjà chez ETIA. Donc, directrice chez ETIA VAO depuis plusieurs années. Et ETIA, évidemment, et VAO, ils développent des technologies de pyrolyse. Donc, pour transformer divers déchets, dont la biomasse. Ici, il y a beaucoup de gens qui sont pour la biomasse, mais on a aussi pour le plastique. Et donc, des technologies qui sont éprouvées depuis plusieurs années. Et on a Stéphane qui développe des compagnies, plusieurs compagnies dans son histoire et qui a son bébé ici, qui est Nellie Technologies, qui existe depuis 3 ans. Et donc, pour faire la capture directe du CO2 dans l'air et le FICO-char qui va vous parler un peu plus tard. Donc, moi, je suis Suzanne Allaire, je suis la propriétaire de Geca Environnement. On a des clients dans 30 pays. On a eu 10 ans la semaine dernière. Et donc, on est une équipe de spécialistes. On a une équipe ici en Europe, on a une équipe en Amérique du Nord, on a des gens Mexique et Canada, et on a aussi des gens en Inde et au Maroc, et ici en Europe. Et ce qu'on fait, c'est qu'on est, dans le fond, on aide les développeurs de technologie, on aide les gens qui veulent consommer du biochar, on aide les gens qui veulent fabriquer du biochar, de la biohuile, du biocharbon, à rendre leurs projets viables économiquement, à trouver des marchés, à trouver les bons prix pour les marchés, et on développe les projets crédit carbone qui vont avec et on commercialise les carbones. Donc, on est vraiment des gens de valorisation du carbone depuis très longtemps. Et moi, personnellement, ça fait 30 ans que je suis dans le domaine. Donc, pas tout à fait récente aujourd'hui. Fait qu'on est content d'être ici aujourd'hui. Donc, qu'est-ce qu'on fait? On valorise le carbone des résidus. Pyrolyse, torréfaction, gazéification, hydrochar, pyrolyse hydrothermique, etc. On ne possède aucune technologie et on est associé à aucune technologie. On a 250 technologies sur notre liste. Donc, quand vous ne savez pas quelle technologie aller chercher, appelez-nous. On développe les projets de crédit carbone. On commercialise aussi les crédits carbone. On peut faire des bundles pour les acheteurs de crédit carbone. Donc, quand un projet est trop petit pour un acheteur, on peut combiner avec d'autres projets. Quand un acheteur de crédit carbone considère qu'un projet est trop risqué, on peut combiner les crédits carbone de différents projets pour diminuer les risques de l'acheteur et permettre aussi aux vendeurs de vendre à différentes personnes pour aussi diminuer le risque aux producteurs de crédit carbone. Et on fait du développement de projets crédit carbone. Donc, on peut critiquer vos projets, vous aider tant au niveau technologie, on a des ingénieurs, on a des agronomes, on a des gens en finance, on a des gens dans le carbone. Donc, on est capable de critiquer aussi vos projets, de vous aider, réfléchir, développer vos modèles d'affaires, etc. Donc, c'est qui on est chez Geca et en fait, nos 10 ans. Donc, on est très, très fiers de ça. Et puis, si vous voulez me contacter, on a un stand ici. Mon directeur commercial il va meilleur parce que je me souviens plus du numéro de notre stand. Donc, je m'excuse, mais on est juste à côté de l'autre salle de présentation. Donc, merci. Je vais donner la parole à Maïté.
Merci, Suzanne. Thank you, Suzanne. I will talk in English because I think it will be easier for my colleague to understand. And I think it will be easy also for French people to understand my English. So I'm happy to be here to talk about the decarbonation pathway that we can achieve through pyrogazéification. I will start with a few words about my company. I'm working for ETIA, which is part of the group VAO. VO is aiming at providing technical solution for waste treatment and decarbonization of the industry. There is 3 main companies inside the group. Scanship, who is leader in providing waste treatment solution for cruise ships. ETIA, who has patented and developed technology for thermal treatment, both debacterization and pyrolysis. And C.H. Evenson, who has joined the group in 2022 and who is developing industrial furnaces. We are around 200 people inside the group, and mainly in Norway and France, but also in the US and in Poland. I say that we are working on decarbonation. There are different ways to do so. We can work on reducing the need for fossil fuel by producing recycled energy from polymeric waste. It's always better to use energy coming from waste rather than new fossil fuels. We work on developing carbon neutral energy by producing renewable energy from biogenic waste. So as you all know, I think here, when we are producing CO2 from biomass, it is considered as neutral because it's the same CO2 that the biomass has taken during its growth. We work on carbon sink through production of biochar. And we promote electrical solution using green electricity rather than fossil fuel technologies. All this decarbonation pathway can be achieved through heat treatment. When we are talking about thermal treatment from any organic product, it can be biomass, it can be waste plastics, it can be tires. If we heat this product with a lot of oxygen, we do incineration or combustion. We produce flue gas and ash. If there is limited amount of oxygen, we talked about gasification. In that case, the objective is to produce mainly gas and ash containing quite a lot of carbon. And if there is no oxygen at all, we are talking about pyrolysis. And in that case, we produce gas, oil, and char. During my presentation, I will focus on pyrolysis solutions. To do pyrolysis, ETIA has developed and patented a reactor which is called Spirajoule. It's an electrically heated screw conveyor. So basically, we have a standard screw conveyor, and we send an electrical current on the screw. Due to the electrical current, the screw becomes hot by Joule effect, and that's how we can convey the product and heat the product at the same time. And with this technology, we can go from 100 to 800 degrees. We can precisely adjust the residence time in the reactor. It's just the speed of the screw that will give the residence time. And we can also easily adjust the temperature just by adding more or less electricity. This technology is integrated in a process that is called biogreen. So when we talk about the biogreen process, we have a feeding system to introduce the feedstock inside the reactor. The Spirajoule reactor, we add a cooling system for the char, because at the outlet of the pyrolysis system, the char is still at maybe 500 degrees, so we need to cool it down to the ambient temperature. And during this process, we also produce a hot gas. This hot gas can be used as it is, but it can also be cooled down and separated between condensable fraction and non-condensable. In the non-condensable gas, we have mainly hydrogen, methane, carbon dioxide, carbon monoxide. In the condensable fraction, it's what we call the pyrolysis oil. We have water, we have phenols, acids, aromatic compounds, stars, a lot of different compounds. And in this both fraction, there is an interesting energetic content, while in the char, we are more focusing on the carbon content. If we go deeper into what happens during pyrolysis, you can see it in this graph. At the very beginning, we have only a solid, 100% solid. And when we will increase the temperature, we will convert the solid into a char. The quantity depends on the feedstock, of course, and the temperature. On biomass, usually, we get around 20-25% of biochar. And if we work on other types of waste, it will be different. We will produce a liquid with a maximum usually around 500 degrees. Afterwards, it becomes cracked. And we produce a gas. The higher the temperature, the more gas we produced, and the lighter it is. With our process, we can easily decide in which part of the graph we want to work. And depending on the business model that we have, we decide to go at low temperature or medium or high temperature. This technology is already available on the market. Here you can see some example of units in Sweden, Canada, or Japan. We can provide bench scale with few kilograms per hour, and we can also provide containerized unit or industrial installation up to 1 ton per hour. Now, what I wanted to do during this presentation was to focus on the decarbonization pathway that we can achieve with this technology through real case studies. So I will present 3 real cases that we have provided and try to show how it can help in the decarbonization. The first one is in Sweden. It's a model biomass to biochar and heat. So basically, we are working on garden waste in this case. At 800 kilograms per hour, we do a pyrolysis with our process, and we produce biochar and renewable heat. Both can be used on the district in a circular economy. What does it mean in terms of carbon? So in these slides, it's not a life cycle assessment. I just want to point out what are the mechanisms allowing a decrease in the carbon emission thanks to this technology. So when working on biomass, the model is for 1 ton per hour because it's easier to compare one model with the other. We have an electricity consumption with our technology because, as you understand, we use electricity to heat the reactor. But in Sweden, the electricity is mainly from nuclear and renewable energy, so the carbon impact is quite low. We produce a biochar. This biochar can be used as a carbon sink. The biochar is really very concentrated in carbon. It's almost half of the carbon in the biomass that can be found in the biochar. And it is in a very stable form. So if you put it in the soil, for example, it will stay there for centuries. And that's why we can really talk about storage of carbon and carbon sink. We usually consider that 1 ton of biochar allows to store 2.5 tons of CO2. So for 1 ton per hour in France, it means 550 kilograms of CO2 per hour that is permanently stored as biochar. As I told you, we also produce some hot gas. In this model, we just burn all the gas and the condensable together to produce some heat or steam. And if we consider that it replaces some heat produced by the combustion of natural gas, we have, again, some CO2 saving avoided compared to the use of a fossil fuel. So quite interesting. We can develop the same kind of model to produce biocarbon and heat. So this is a second case study. This time we are in Norway, and we are doing pyrolysis on a wood. It's a residue from sawmill. In order to produce, on one side, some heat that is used to dry the biomass, and on the other side, we produce biocarbon that can be used in steel industry. You may know that in the steel industry, the carbon impact is quite important and need to be decreased. And replacing the fossil coke by biocarbon is one pathway to reduce the carbon impact of this industry. What does it mean in terms of carbon? One again, if we introduce 1 ton per hour, here in Norway, the electricity impact is even better than in Sweden because it's mainly hydraulic. We produce biocarbon. We need to pelletize it before being able to use it. And it comes as a substitute of fossil coke. we consider that 1 ton of coke is responsible of 2.3 tons of CO2. So that is CO2 that can be avoided by using this product. And in that case, we cool down part of the gas. We use the condensable as a binding agent during the pelletization. And we burn the remaining gas to produce heat or steam as for the previous model. So once again, it's a CO2 saving compared with fossil fuel. The last case study that I wanted to present is a bit different. It's on waste tires. So it's not biomass, but still it works. In that case, we do pyrolysis on waste tires. We produce a biochar that is not really biochar. It's, in that case, recycled carbon black. It's a concentrate of carbon that can be used again to produce new carbon instead of using virgin carbon black. And we produce a fuel and a gas that can be used as a fuel and heat. In terms of impact, for this case, we are in England, where the electricity is still linked to natural gas, so the carbon impact is higher. We produce some recycled carbon black, and usually we consider that it divides by 4 to 5 the emission compared to virgin carbon black that is produced from fossil fuel. And we produce a gas. In this model, we will condense the gas in order to get the liquid fraction because it's very energetic and it can come as a substitution for fossil fuel. And we produce, again, some heat with the non-condensable fraction. In that case, the feedstock is not biogenic, it's waste, so it's only low carbon product. But what is interesting here is that in the tires, part of the tires is still biogenic. And we have done some analysis showing that this biogenic fraction is not recovered in the carbon black, but it is recovered in the oil and gas. So even in this case, we have around 40% of the fuel that is biogenic and leads to neutral CO2. So a quick conclusion. As you all know, decarbonation is not an option, it's a necessity. And pyrolysis is a flexible and already industrial tool to achieve this by production of carbon sink, by reducing the need for fossil fuel, producing carbon neutral energy, and using green electricity. If you want to know more, we have a stand in J41, so please visit. You still have all the day tomorrow. Thank you.
Yeah, thank you, Maïté. So we'll ask question after. I will let maybe you go. Okay, we let's go with question then.
Thanks very much for the presentation. I know it's a usual assumption that the carbon neutrality of biomass, but as you may know, it's less and less the case. First, in time, because of course you will release CO2 that has been eaten, let's say, before, but still in the coming times it will mean release of CO2. And second, because of the level, as you know, the forests are degrading more and more, and even for sure you will not recover all the CO2 that has been released. So I understand it's the usual assumption, but I'm afraid it's less and less accurate and real. So I don't know if you have a comment, because I guess in the coming times this will come into play. I mean, the assumption of carbon neutrality of biomass will not be considered anymore, I'm afraid.
Yes, thank you. It's an important point. It's true that if we do a complete carbon assessment and life cycle assessment of the process, we may have to decrease these assumptions. But still the mechanism is still here, and I think that the carbon impact will be better using biogenic product rather than fossil fuel, even if we add a percentage of non-fully biogenic or neutral carbon. Yes.
Any other questions?
Thank you.
Thanks.
That was great. I don't know how to follow that one. I have notes, which is no good. Bonjour, je m'appelle Steven et mon français est assez mal. Donc, je voudrais parler l'anglais maintenant, s'il vous plaît. I'm Stephen Milburn, and I'm the founder at Nellie. And I'd like to tell you about the dirty business of building a technology that fixes the climate. Now, my team and I have spent the last 3 years designing, developing, and deploying a bioengineered carbon dioxide removal system that uses an innovative microalgal growth system to capture carbon dioxide from ambient and industrial sources, and we then sequester that captured carbon as biochar and biogenic aggregates. It's a new technology that we have built to mitigate against the very worst effects of climate change. Now, I'm a physicist by training, not a bioengineer, but I like to think of myself as a founder by trade, because I've been doing this for a long time, as you can tell by the lines in my face. Since I was very small, I knew that I wanted my own company. I love physics and I love science and I like building things in my garage, but the startup capital needed to build a business in physics and buy a nuclear reactor is really, really high. So I lowered my ambition a little bit, and my first business was in haulage and logistics. Now, back then, running a fleet of trucks was not quite as expensive as it is now, but still, the purchase of fuel for those trucks was really, really, really expensive. So I stupidly thought, well, surely there must be a way to make biofuels on site at our garage to put into our trucks. Now, I can see, and I've spoken to a few people today who know of businesses that have died on the altar of making microalgal biofuels. But bear with me, I will get to the point of why. So knowing something, but not too much, about the biofuel potential of microalgae, I set about building a prototype photobioreactor. A photobioreactor is the machinery in which you grow microalgae in an aquatic solution. It was astonishingly a little bit successful, but as a lot of people in this hall today know, totally economically unfeasible. So fast forward a couple of years, and I'd exited my haulage company, and I was driven by the desire to work from somewhere else in the world because the UK is really wet and not warm. So I thought, if I create a software company, I can travel the world with my laptop. So about 15 years ago, I started TradeBox, which is still in operation now back in the UK. We have a really nice portfolio of industrial software clients, and yeah, it's a really nice team. Fast forward a few more years, and we get to COVID. And I think, like many people, the pandemic gave me a chance to reflect on what I was doing professionally. And I realized that whilst the last 10 years had been somewhat profitable, they hadn't necessarily been as purposeful as I would have liked. And I was in a conversation with one of our clients at Tradebox, and that company was heavily involved in the Swedish emissions trading scheme, which was even more efficient than it is now at the time. And this company needed a way to decarbonize their operations in the UK, and they needed it quickly, and there wasn't really anything on the market that could do that. So I thought, well, how can I help with that? And I didn't want to do a software product. I wanted to get my hands dirty and build something. Whilst I didn't have a strict engineering background, I think I had just enough knowledge to try and fix the climate. That's really arrogant to say, isn't it? But that's where we are now. We are an operational, commercialized carbon dioxide removal system at 100 tons of CO2 removed per annum from our site in South Wales in the UK. Now, I thought I knew a thing or two about business. I think the theme of arrogance is coming through quite strongly. But building a hardware company to address a new market has proven me incredibly wrong. I naively assumed that because the need to fix the climate was so very, very urgent, that building the technology would be the hardest part of building Nellie. I incorrectly assumed that if I built it, that the customers would just start flowing through the door to buy our carbon credits. I was really, really wrong. That the main challenges involved in building a climate tech company are not the technological challenges, but they're the operational and commercial challenges faced by any other business that I'd been involved in. So I'm going to tell you about these challenges that we faced at Nellie, and more importantly, I'm going to tell you how we've tried to overcome them. Now, the first challenge we faced is in compliance, and in that I mean not just operational permissions, but the freedom to operate and our intellectual property. We did not have the time to build something that would require specific operational requirements from our local environmental health, which is the authority back at home who gives us the permissions to operate. Also, we did not have the money to build an entirely proprietary IP portfolio from scratch, or, to be honest, the motivation or the patience to deal with technology transfer officers in academia who, at the time, held the state of the art. Capital was always going to be a problem. Most VC, at the scale that we were at 3 years ago, is really, really impatient, and if you'll forgive me for saying, often has ideas on scalability that are applicable to digital and software products, but not really hardware products. Our runway at Nellie needed to be really quite long, not just turning a profit in a year or 2 years. We probably needed to be a runway till now. And the VC market at the time just wasn't geared up to fund us for that amount of time. And you all know, or many of you will know, that building what is in essence a biorefinery from scratch is really quite expensive. So how could we build something that worked within our really small budget? And finally, customers. That's the age-old problem. How on earth we were supposed to find buyers for something when the technology didn't exist yet, in a market that didn't exist yet, and where the policy supposed to be driving that market didn't exist yet. Now, none of these barriers could become blockers, and every one of them had to be overcome, or we simply would not have a business. And to make sure that we could operate, we built a system within existing operations frameworks, which at a high level means basically we built a food production system. It's something that our local authorities understand, and they see how we've minimized our operational risks. For the IP, for our intellectual property, as I said, we couldn't entertain dealing with the state-of-the-art holders. It was just a non-starter. The percentage of our company that they would want to license their technology to us was just unconscionable. So we built our own IP portfolio. We got some really cheap lab space. We had some small grants coming through, and through continual R&D over the course of 2 years, it meant that we could become the state-of-the-art in microalgal growth technology. And then the capital, that came from grants, and lots of them. I think that's my second speciality now. I know an awful lot about building photobioreactors, and if anyone wants to talk about how to submit grants, then I'm also your man. We identified where our plans for fixing the climate aligned with the strategy of local, regional and national funding pots. So small pots, not horizon level projects costing €5 million, much, much smaller than that. And that meant that we could build our systems through continual R&D, and that's something that we continue to do today. And finally, customers. It's almost certainly the biggest barrier in a new market is finding your customers. But that is something that I know a little bit about. And we addressed this nascent market by selling like an SME. And nimble business has always been in my blood. I've never ran a multi-million pound company. It's always been smaller than that. And I couldn't, and I still can't see why selling carbon dioxide removal certificates, selling biochar, selling our biogenic aggregates should be any different to that. And now selling like an SME to me, and I know it means different things to different people, but it means selling quite aggressively. We call it in the UK a chamois leather salesman, knocking on the doors until you get that sale. And that's really what we've done. We've identified our funnel of prospective buyers. We've thinned them out quickly to make sure that we're only talking to the decision makers. And most importantly, we've taken every single step we can to get our technology in front of those buyers. And that means getting them to our pilot site. And if they can't or won't come to our pilot site because it's not in the southeast of England where everyone likes to live and do business, then we built a mobile direct air capture unit. And that just rolls off the tongue. We're still working on what to call it. But we'll drive that mobile direct air capture unit to their offices and park it outside so they can see and smell and, if they so wish, taste our technology. And then we try and sell it with as much passion as we can muster. We've built something that offers a practical and purposeful way for organizations to reduce their emissions profiles. I believe in it, and I think we're proving that the market believes in it too. Only last week, we were really pleased to announce that we've entered into our first major offtake agreement. Zurich Insurance has contracted Nellie to remove nearly 20,000 tons of carbon dioxide from the atmosphere within the next 5 years. So, what did Zurich see when they came to our pilot site that gave them enough faith that we can do what I am saying we're doing? Well, first of all, they saw our new technology in action. It smells. I mean, it really stinks. Is there anyone here who works in phycology and microalgae or a dirty biorefinery? You know, if you come to our site, you will leave smelling bad. It's noisy, and it did provide them with all of the proof points that we needed in our rather ramshackle operation. I refer back to Maïté's presentation where the technology is like leagues above what ours looks like. I mean, look at that there. But more than that, though, it addressed several of the pain points for Zurich, namely that it provided them with a long-term supply of verified carbon dioxide removal credits at a price that they could lock in now, and it gave them the proof points that only a very physical and very quantifiable direct air capture installation can provide. From a technical perspective, I think what we've built at Nellie is an exercise in bootstrap bioscience and bioengineering. Our granted patent, which is the only one we could afford to do so far, is in the field of growth enhancers. We have a synergistic combination of ferrous particles and mycelium, which when used together in the way that we use them together, increases the photobioreactor's efficiency above the state of the art. We have a lot of black box technology, which we can't afford to patent just yet, or we will be patenting this year. And that includes a photonics propagation kit, which is my background in physics, and an electromagnetic growth enhancer. Now, we have a film that was made by the Chinese news channel, CGTN, that's on YouTube. It's 30 minutes of me basically saying this again. It can be quite boring, and you've gotten the preview here. But the first comment on YouTube was, this guy has some lights and a magnet and he's calling it new science. Now, that man, cruel as he was, is not entirely wrong. It is far more complicated than that, but what we have is a synergistic growth enhancer, a fancy magnet which operates in a proprietary way, and some fancy lights which operate in a proprietary way. Our systems have grown from some tubes stuck in some second-hand wire mesh to become a modular, scalable, and geographically agnostic carbon dioxide removal technology. We've been operational for over 1,000 hours now on the pilot site, and we've removed over 100 tons of CO2, and we've produced nearly 35 tons of biochar in that time. Our systems are robust, reliable, and repeatable. And crucially, it will scale. We built Nellie to address the climate crisis now, not something that you have to wait 10 years' time for. Our systems work to do the job that they were built for, and we're not going to stop trying to realize all of the operational efficiencies we can within the system and accessing the adjacent revenue streams that our technology can provide. We're actively exploring the potential of our tech in feed, fuel, and fertilizer applications. And right now, we have a test farm back home trialing several blends of biofertilizer, a pilot on biochar for remediation, and only last week, a sensor project delivering data to develop an innovative monitoring, reporting, and verification system. Now, all of this R&D doesn't divert from our roadmap, it strengthens our roadmap. It means that we have a viable route to scaling our systems to over 100,000 tons of carbon dioxide removed every year by 2028, and realizing all of the environmental and socio-economic co-benefits that go with it. It means that by 2030, we will have built something that's hopefully globally transformative with our future licensing and deployment partners. And the key there is partnerships. We could not have got to this stage alone. I am both morally and contractually obliged to thank our funding and support partners, but really, I am incredibly grateful to them because we couldn't have bootstrapped this together without them. I'm grateful to Paul and the team at Bio360 for having me speak here today. And I'm really grateful to you because you could all be in the pub now. I mean, this is the death slot, isn't it? It's the last one of the day. So you could be elsewhere having much more fun. No, I mean the last session of the day. Yeah, I'm not the last, but the last one of the day. And I've got one more thanks, which is to those of you who have listened to me prattle on for the last 10, 15 minutes, is that you will help me spread the word of what we're doing at Nellie, that you will take away that these technologies can be built and can be scaled to fix the climate. You are all welcome to come and visit our pilot site in South Wales, or our future site, which we'll break ground on, also in South Wales in June of this year. If you do come, and you are all seriously very welcome, don't forget to bring your Wellington boots, because fixing the climate is a really, really dirty business. So thank you for listening. If you've got any questions, I'd love to take them.
Thank you. Carbon removal using microalgae is usually considered as very expensive. What is the... You did not mention the cost, if I'm not wrong. Well, what is the cost of the equivalent of removal of 1 ton of CO2?
Well, can you hear me? I mean, I've been asked this question an awful lot, and I think it's really rude. I mean, you're basically asking our margins, right? And that's between me and my God. No, but I mean, what we trade at, and you're right, carbon dioxide removal using microalgae is really expensive to grow if you do it the old-fashioned way. We do it in a new way that we've developed this technology specifically for. And the reason it isn't, there's no Nobel Prize in this, it's a good technology, but the reason no one else has done it before is because other microalgal phycology businesses are really focused on nutrient extraction, and to get the nutrients out of your microalgal growth system is really costly, but your microalgae have to grow in a certain way to do that. We're not bothered about nutrient extraction. If we can realize that revenue stream, fantastic, but it's not our prime purpose. Our prime purpose, and I'm always really open about this, if you look at any other biochar producer, they tend to have a biomass feedstock supply stream that at the moment can be quite good because it's waste wood or whatever you might be using, but in 2 years' time, in 5 years' time, the next time there's a war on the borders of Europe, that waste stream becomes a commodity. And how do you still have a business if all of a sudden your biomass that you're putting into your system is 10 times more expensive than it was when you started? So we're entirely focused on building something that will be stable for the next 10 years, the next 15 years, by doing as much as we can to reduce the cost of that microalgal growth. So I won't tell you our margins, but I can tell you that we're trading today. If you wanted to buy 1 carbon dioxide removal certificate from us today, it would be around about 500 euros. Which makes us one of the world's most expensive biochar producers, but one of the world's cheapest direct air capture CDR providers. In fact, if not the cheapest. So there's a double-edged sword, but yeah, so that's what we do.
It works. It probably. Can you hear me? Yes. Okay. Okay. So good evening, and thank you for still being here. I know you're probably tired, but I'll try to make my presentation interesting enough. So my name is Filippo Munna. I'm Sales Director at Hexagon Agility. We are a Norwegian company specialized in designing and manufacturing high-pressure composite material cylinders and systems for compressed gas transportation and distribution. I'll talk more about the company. I just would like to say that our heritage is in the aerospace industry. And just to give an example, for those who remember the space shuttle in the 80s, all the composite material, high-pressure tanks on the space shuttle were manufactured by one of our sister companies, back then called Lincoln Composites, part of General Dynamics. Today it's Hexagon Lincoln. So we have an heritage that dates back more than 60 years ago. Should I push this one to move forward? Okay. Okay. So let me start with the question, how many of you know what is the annual consumption of natural gas globally? Okay. We are talking about 4 trillion cubic meters of biomethane globally, of natural gas globally. But then when we look at the potential for biomethane, it's almost 1/4. So it is a lot of gas, and most of this is carbon negative, as we will see in a moment. Well, how many of you have a sense of how much biomethane we are producing today per annum? It's about 44 billion cubic meters, so nothing. We are literally just scratching the surface, as my slide says. You know, there's a huge potential, and this goes both in the direction of offering energy security, which is a topic here in Europe, clean fuel. I mean, biomethane is carbon negative, and we're not using it. So let me focus on Europe, since we are in France. Today in Europe, we produce 23 billion of biogas and biomethane. When I talk about biogas, I refer to the products, the output of anaerobic digestion, so 40% CO2. Actually, if I limit my number to biomethane, it would be around 5 billion only. Where the potential would be, this is an estimate by the International Energy Agency, the potential, considering the available feedstock, would be 127, which is around 16% of the energy consumption of the European Union. Now, we are all concerned about our energy security, which is also threatened by the war, just to say one, and actually we are not using what we have in-house. Most importantly, I would like you to focus your attention on the 65 billion that could derive from agriculture feedstock, so animal manure and agriculture residue. And by the way, these figures include UK, so it's not only European Union, it's the whole Europe. So when we talk about agriculture feedstock, then this is what we get. We get an average carbon negativity of minus 330 gram of CO2 equivalent per kilojoule, which is the estimate made by the CARB in California. Now, what happened in California is that you can trade your biomethane based on the carbon negativity of the fuel, and that allows for increasing your price if your operation is really, really good. Now, I go back to my previous slide. Half of the biomethane that we could potentially produce is carbon negative. There is no such a fuel at the moment. Even hydrogen is at most slightly carbon positive. So this biomethane is really the what we can call the magic fuel. And I would like to cite another challenge that we have in Europe, and it's the problem we are having with the agriculture sector. You know, we have seen it last winter. Biomethane could be a source of revenue for farmers. You know, I mean, they have residues that could be turned into fuel. Now, we, as Hexagon Agility, we think we have a very good solution, especially for especially for producers of biomethane that are located away from the grid. And I go back again to biomethane produced with agriculture feedstock, which are normally produced away from the grid. Now, of course, you can take the feedstock, you can take the animal manure and move it to a biomethane plant that sits on the grid and then inject the gas in the grid. But then you have the cost of moving the feedstock, and also your CO2 emissions will go up. That's why normally you like to produce your biomethane where the feedstock is available. And then you probably have to compress the gas and bring it to an injection point. Why am I saying that Hexagon has the right solution? We are manufacturers of composite material, high-pressure cylinders and systems. That means our product is extremely light. When I take a high-pressure cylinder made out of steel, I'm talking about a product that weighs, give it or take, 1.2 kilogram per each liter of hydraulic capacity of the cylinder. And this is how the compressed gas industry has developed. You know? Gas has been moved in compressed form by means of high-pressure steel cylinders that are very heavy. But it works well, and the problem is that you are moving a lot of steel and very little gas. It works since over 100 years. Our cylinders are made of carbon fiber. Their weight is approximately 0.25 kilogram per liter of hydraulic capacity. So it's over 80% lighter than the equivalent made out of steel, which means in the end, the bottom line is we can move with the same container full of cylinders, we can move up to 3 times the amount of gas that you would move with traditional steel. We all know that there are limits on road. In Europe, it's about between 42 and 44 tons. And that's why if you have a very light product to move the gas, then you can transport gas and not steel. We have deployed our products more or less globally, and we serve filling station. We bring gas to injection point in the grid. We bring gas to industries. We deliver gas as a maritime fuel. This is what we do. These are images of our containers. The one at the top right corner shows 3 20-foot containers carrying over 15,000 cubic meters of biomethane in Sweden. We have an Air Liquide operation. I'll show a video in a moment. And the container at the bottom left is moving gas in the US. But we also have marine application. That's why I like to show the photo of this ship, which is called Kairos and utilizes our cylinders as a fuel storage. So before I show a video that perhaps is self-explanatory and works better than me trying to explain what we do, do you know what's the annual? Probably this is difficult. What is the average annual consumption of a French home? It's 18,000 kilowatt hours. Now, when I take an X-Store, which is basically one of our containers full of composite material cylinders, this container carries around 13,250 cubic meters. Let me show it. And that, in terms of energy consumption, could hypothetically serve 380 French homes in a week. Just to give the idea of the size of the storage that we manufacture. This is the video. It shows an operation in Scotland. We basically serve 4 distilleries of Diageo across Scotland by means of our containers, and well, the video works better than me explaining it.
One of the biggest malt whiskey brands in the country. We're about number 4 or 5 in the world. Sustainability for us is about a profitable business, a planet that is protected, and our communities and people that we work with. This is a remote location, north of Inverness. There isn't much infrastructure.
Air Liquide does two things. On one hand, we produce biomethane out of biogas, which we take from anaerobic digestion plants. And on the second hand, we supply biomethane to industries for industrial applications. Here at Glamorungi, we have proposed a solution where we bring compressed biomethane from a station in Fordoun because the distillery is basically off the grid. We have to deliver gas on a continuous basis to Glamorungi 24/7, 365 days a year. We built a station for the customer, which we own and operate, and the station delivers on average about 450 cubic meters per hour of gas to the distillery. The trailer comes in full, and the driver will unload that full trailer into pressure reduction station while taking off a trailer which is empty, and we call that a swap.
It's a much better option than many of the alternatives we have, such as burning oil or diesel. I do believe for remote communities or remote sites, if you have enough demand, it's a really valid solution. And certainly for us, it's been transformative.
Okay, so perhaps, do you? Okay, now you can hear me. So basically the idea is to have a virtual pipeline and move gas in compressed form. That is very easy to deploy. You will have it in operation in less than a year. And of course, it requires less capex than having to build a pipeline. And it's also more flexible if one day you need to redirect your gas supply to other customers, you can always do it. These are definitely the highest capacity containers for compressed gas transportation available today in the market. And a little bit about Hexagon. I mentioned at the beginning, and then I moved to the product. So Hexagon, as I said, it's a Norwegian company. We are really inspired by the idea of clean air. So we have a company that is fully dedicated to hydrogen distribution. It's called Hexagon Purus. The company that I represent, Hexagon Agility, is focused on biomethane distribution. When we say that we are driven by the passion of driving energy transformation, we really testify it with our actions. For example, in North America, the whole structure of rules and regulation for compressed gas transportation has been driven by Hexagon. So we have a team of persons that talk to governments and help also building what are the rules for the dangerous good transport. The company has a turnover of around €500 million, is listed at the stock exchange market in Oslo, is by the way shared by our major shareholder is Japanese, it's a company called Mitsui. And like I said earlier, our heritage is in the aerospace sector. Now, what I'm presenting is quite innovative, but it's there since already 20 years. Okay, we have put over 2,000 of these containers in the field between North America, Europe, Middle East, and Asia during the past 20 years. We have over 100,000 vehicles utilizing our lightweight storage because, yes, these cylinders can also be used as a storage for fuel. I showed the ship in my second slide, but we, until, let's say, the green transition decided to stop the use of gas for transportation, we were the sole supplier to Volkswagen for storage of CNG in their vehicle. And today we serve Iveco, we serve Scania, we serve all the major manufacturers of trucks and buses with our system. In North America, we have over 75% of the market share for systems for trucks. And these are examples of our stories of success. It's not only always biomethane. What you see here are also examples of compressed natural gas being moved with our products. But the benefit is always the fact that you can save on CO2 emission. You are moving, let's say, 3 times the amount of gas that you would move with traditional technology, which means then in return, you burn less fuel for moving the gas. This is a glance at the cylinder. The cylinder is basically a plastic liner wrapped with carbon. It is not only very light, it is also non-corrosive, It has unlimited ability to cycle. It suffers of no fatigue. It is leak-free. It behaves very well in case of fire accident because the liner melts and there is no way that the cylinder builds pressure in a bonfire. So I'm about to close. One last question, just to give the sense of what we do. What is the longest mobile pipeline that we run in the world? We have it in North America, here where we move helium between Canada and the United States, and the gas is transported through a route of 1,700 kilometers. I must say, in Europe, we have a very good business case already when we have to move gas through distances between, let's say, 15 kilometers and 100 kilometers, because that will be the case in Europe. The grid is very well developed and distances are not big. But outside of Europe, we really, I have recently acquired a project in Jordan. We move gas from the border with Iraq to the capital Amman. It's 100,000 cubic meters per day through a distance of 350 kilometers. So this chart gives the idea of the performance of composite material cylinder. We sit in between traditional steel technology that works very well and the distance is super short, because steel is cheaper than composite, so the price of our product is higher than the one of traditional steel. So if the distance is 5-6 kilometers, then your operating cost will be very low, and you may not care about maximizing the amount of gas that you move per load. But when distances in play are between, say, 15 kilometers and 500 kilometers, and the amount of gas that you're moving is between 10,000 cubic meters per day up to, say, 600,000 cubic meters per day, we have a very good business case with our composite material technology, which is, in fact, the industry calls Type 4. Above that, that is the kingdom of liquefied natural gas or liquefied biomethane. So we are not trying to compete. All I'm trying to say is that we have a field of application that works very well and where we can demonstrate that we have a very good business case. But to wrap it up, let me talk about Europe again. You probably know that the European Union has set a target at 35 billion cubic meters of biomethane per year. We saw earlier that the potential is 127, and today we are making only 5. Today we are only making 5. These 5, if I include, let's say 23 billion including biogas, accounts for only 3% of the energy demand of Europe. Hexagon, with this mobile pipeline solution, could really be the key to bring Repower EU to fruition. And thank you.